All right, everybody, I think I'll go ahead and get started here. It's about 10 o'clock. I know it's really hot outside and there's a lot of challenges finding parking and so on this first part of the semester. So maybe people are going to trickle their way in soon. But I do want to get started because we have a lot to do. We always have a lot to do. Just a couple quick announcements here. First of all, there is a homework assignment due tonight. I'm going to start off today taking a couple questions off of that. And then don't forget, I have office hours throughout the day later on, right after class, and then also tonight, a couple of sessions in the evening, all the way up until 10 o'clock. And you don't have to turn in the homework until midnight, basically. But try to get that done. There will be another assignment coming right around the corner. Remember, we're playing catch up a little bit, me being gone last week. So the next assignment will be covering the Bernoulli and homogeneous differential equations that we did on Tuesday in class. And as of right now, it says that it's due on Sunday evening, I believe. I'm probably going to move that to Monday because I don't think I'm probably going to be able to have the Monday office hour. Remember, it says I have office hours on Sunday and Monday usually. This coming weekend, that will probably be Monday that I can do it, maybe not so much on Sunday. So what I'll do is probably move the homework to be due on Monday so that you can ask me questions in my office hours before you actually have to turn it in. So I'll make that little tweak to Canvas before before I get too far through the week here. But that's about all I have for announcements. I am going to take attendance here in a few minutes. I think I'll wait until more of the crowd can get here so that I can just make sure I'm checking people off that are trying to be in the class. So we'll do that. But other than that, does anybody have any other administrative questions before we dive into some math here? Yes, Audrey.
Is there any way we can
I don't mind what your so she's asking me about the submissions of the homework. The main thing is I want one file. It has to be one file. It has to be compiled into one file because every time I have to click to open something, it spins and spins and spins. And so if a student sends in 10 pictures that are on 10 separate files, that will take much longer to grade than if it's one thing. So that's the only thing. I don't really care if it's a PDF versus a JPEG versus a different file format. But yeah, do your best with that for me. Thank you so much. Anything else? Okay, let's take a look at a couple of the problems from tonight's homework. I know maybe not everybody has fully completed the assignment yet. That's fine. And if my grader happens to pick these problems to grade, then as long as you're writing down my solutions, you should be in good shape on those. I don't know. My grader, I don't tell my grader which problems to grade in detail. He picks the problems he wants to grade, and sometimes, you know, he may pick the same ones that I've already covered in class. Who knows? These are problems from section 1.4. This was the section about separable differential equations. So of course, in this section, we're probably expecting everything to be separable. Later on, of course, we have to get good at figuring that out if they're scrambled up, right? Because there could be a separable one side by side with the Bernoulli differential equation, side by side with a linear one. They can get all scrambled up. But in this section, the focus is on the separable differential equations. So let's take a look at this example right here, number 12. It's the quantity x squared plus 1 times y prime plus y squared equals -1. And there is an initial condition. If they ever give you an initial condition, just remember that that can be kind of set off to the side until the very end when you've finally got the general solution. You can then solve for the constant that shows up there. Okay, so this is the idea. So let's focus on the actual differential equation first. And if I wanted to get that separated, because as of right now, it's not really separated, can somebody suggest a step I could take that would help me get this separated?
Divide.
Pardon? Dividing x squared plus 1. What were you going to say? Okay, we'll rewrite the y prime as dy dx. Maybe I'll do that first. So let me rewrite y prime as dy over dx. I like to express it that way. You could divide through by x squared plus 1, and in fact, eventually we will. But there's something else I might do first. Yes.
Subtract the y squared to the other side.
Excellent. I would probably subtract this y squared to the right side first of all. So let's do that. I'll leave the left side the way it is. And when I do the subtracting, I'm actually going to factor out the minus sign. So it'll be negative of the quantity of y squared plus 1. Okay, so just a little bit of algebra here, right? And can I get the x's and y's separated pretty easily from here? It's not too bad, right? Now we're going to divide through by x squared. We're going to throw the dx to the other side. And we'll take the right-hand side and put it underneath the dy. Let me just do all of that kind of in one step. So we'll have a negative of, well, actually, let me just leave the minus sign where it is. So I'll divide the y squared plus 1 underneath the dy. I'll leave the minus sign over here on the right side. It doesn't actually matter, but I'll just make my life a little easier if I leave the minus sign on the right side. So it should be something that looks like that. Yeah, dy divided by y squared plus 1 equals negative of dx divided by x squared plus 1. Remember, you should never have a dx or a dy that is underneath a fraction. So as you're dividing things across these equations, you don't want to end up with dy underneath or dx underneath. They need to be upstairs always, because of course, once I integrate both sides, which is going to be the next step, you can't have an integral, like in calculus, you never saw an integral where there was a dx underneath a fraction, right? That's not the way you would notationally expect to see it. So we'll make sure we leave those dy's and dx's upstairs. Now, does anybody know the antiderivative of y squared plus 1? It's the arctangent of y, right? So if you didn't remember that, it's in the table of integrals that's in the book. It's not one that most people need that often, but yeah, this one is just the arctangent of y. And this is now going to be equal to, notice on the right-hand side of the equation, I have a minus sign. But other than that, I have more or less the same integral to do. And so this one is going to be the arctangent of x. And have I done anything wrong so far? I need to add the plus c, exactly. So don't forget to add c, and we don't need to do it on both sides. So you can just go ahead and put that constant maybe on the right-hand side like so. It's a good idea. And so this is what we would have. This is what would be called an implicit solution to the differential equation. We have not yet solved for y. If I wanted to solve for y, what would I think about doing here in this next step? Take the tangent of both sides. Exactly. I'm going to kill this arctangent by applying the tangent function to it. So if I do that, y will be equal to the tangent of the negative of the arctangent of x plus c. Notice I'm using a lot of parentheses around this. And I know it's tempting. I know it's tempting to sort of cancel the tangent and arctangent right here. But be careful with that because, first of all, there's a minus sign in the way. There's also a plus c. We cannot just throw the plus c outside on the far right. You have to leave it where it is. So my recommendation right now, guys, is don't try to simplify it at all. Okay, just leave it the way it is. It should be just fine. Okay, so we do that. This is what's called the general solution. And am I done? No, why am I not done?
We can solve for c.
Exactly. We can actually solve for c by using the initial condition. So in this case, we can derive a particular solution to the differential equation by using this initial condition. What this says is that if we plug in an x value of 0 into this expression, the y value should be equal to 1. So I'll go ahead and put the y value for 1, and that should be equal to the tangent of negative of the arctangent of 0 plus c. Does anybody know what the arctangent of 0 is? In other words, what angle, if you take the tangent of it, would the answer be 0?
Pi, or is it?
I have to remember, I haven't taught trig in forever. But one of the branches of the tangent graph, you know how that graph kind of looks like this, then there's a bunch of other branches along here. Anyway, you can see right here, so if this is the graph of the tangent of x, it goes through 0, 0. It actually goes through 0, 0, which means that the arctangent of 0 is just 0. So if you plugged in 0 into the tangent function, you would get 0 out. So just reversing that, right, taking the inverse function, then that output of 0 becomes the input to the arctangent function, which would have an output of 0. So this is just 0. So this just becomes 1 is equal to the tangent of C. And now I have to ask you one more trick question. Does anybody happen to know what angle has a tangent value that's equal to 1?
45.
One more time?
45.
45 degrees, yeah, which is pi over 4 in radians. It's exactly right. So this tells me that C is pi over 4. Don't get too worried about all this trig stuff. It's not going to come up very often, but in this case, the C value is pi over 4. So to write down the final answer, then you would just go back to your general solution, which was this one, and now just plug in the C value just so it has a finality to it here. So y is equal to the tangent of negative of the arctangent of x plus pi over 4. That would be a great answer. Okay. Question, yeah.
So we should keep it in radians?
Yeah, radians is a better unit of measure to use generally because things like the derivative of sine being cosine, that works great for radians, but it's not true in degrees. So yeah, we should use radians if possible. Okay, good question. Yes,
What are the chances that we're gonna see like trig identities, like, you know?
not too much like this kind of stuff, especially tangent functions. I mean, I expect people to know a little bit about sine and cosine, but this one I wouldn't lose a lot of sleep over it. I don't think you need to spend the weekend like reviewing all of your trig values and so on. It's not really the key thing at this point. Okay, everybody okay with that? Any other questions on that one? That's number 12. Okay, awesome. The other one that got up onto my board over there is number 26, which is a completely different kind of problem. This one is actually a word problem about trying to establish the time that a murder happened. So they have this setup where, you know, the temperature outside is 34 degrees. I think they told you that as a value. So that's called T sub m, the temperature of the medium. So we're already thinking about Newton's law of cooling here. And so that's the temperature of the medium. And then what we know is that at 2 o'clock, they found the victim, and then the victim's body temperature was 38 degrees. And then 1 hour later, the body temperature had dropped to 36 degrees. Of course, it's going down because outside is only 34 degrees. Right. And so if we know that the normal body temperature is 98 degrees, then the question is, well, what was the time of the murder? And so we can try to use Newton's law of cooling to do that. This problem, we actually don't have to do any solving of differential equations because with Newton's law of cooling, I already did it in the videos that you watched last week, right? So Newton's law of cooling, we could go through the motions of solving it again, but it would be literally the same thing I've already shown you once before. So I would rather just go straight to the solution to the Newton's law of cooling differential equation, which I'll remind you here what it is. The temperature of the object at time little t is T sub m plus a constant that in my notes I eventually labeled as C2 times E to the negative KT. So I'm hoping that this is looking a little bit familiar from the notes from last week. I would rather not rederive the whole thing right now. That's the solution to Newton's law of cooling. Now, of course, I can put in 34 for the temperature of the medium already. That was given to us in the question before we even started. And then we still have two other constants here that we don't know, the C2 and the K, but we also have two other pieces of information that we haven't used yet. Okay. So the key thing here, guys, actually is to, well, there's no right answer to this or wrong answer to this, but we have to sort of decide when or at what time will the little t be equal to 0. Like this time here that shows up in the formula, that's time. And how is that time running as compared with the information that they gave us, right? So my advice in order to make everything work out the easiest, my best advice is going to be to set 2 p.m. to be the time of 0, because that's the first time that we actually have a value that we know. You don't have to do that. You could decide to set t equal to 0 at any time around the clock that you wanted, and you should still be able to get the right answer. It just won't be quite as clean to do so. Okay, and then I would also want to mention here that I'm going to measure t is going to be measured. I would recommend measuring it in hours, since we're kind of being given information on an hourly schedule, right? 2 p.m., 3 p.m., so on. So I think doing it in hours would make the most sense. Okay, so all we really have to do, guys, with this is there's not a lot of actual Math 250B on this. This is mostly just high school algebra problem, because what you're going to do is just put in 0 for little t, and then when we get to 3 p.m. we'll put in 1 for little t, and kind of crunch the numbers with this thing. So let's do that. Let's put t of capital T of 0. If I put in 0 for the little t, what is e to the 0 equal to? 1. Just 1, right? So that's just 1. So then what are we left with? We're left with 34 plus whatever C2 is. So this is 34 plus C2, and I'm going to set that equal to what T of 0 is supposed to be, which is that the temperature of the object at 2 p.m. is supposed to be 38. So I'm going to set this equal to 38 right here. Everybody following that? I'm going to put in 0 for little t, and we get 34 plus C2, but we also were told that that temperature should be 38. And you can just immediately see from here that we already can solve for C2. C2 is going to be equal to 4. Pretty straightforward. Okay. So that's the C2 value. We also have to figure out K. And to do that, we're going to use the other information, which is they told us what T of 1 is. At 3 p.m., which would be 1 hour later, right? We can figure out what's the temperature of the body. So this is 34 plus 4 times e to the negative k, right? So I'm just putting a 1 for the little t right here. So I just get 34 plus 4 e to the negative k. Remember, C2 is equal to 4. And this is supposed to be set equals to 36. Because they told us at 3 p.m. the temperature was 36. So this is plugging in T of 1. At this point, we can subtract the 34 into the 36 and then divide through by 4. So if I solve that, I should get e to the negative k is equal to 1/2. Check me on that. Make sure that my math is clear so far. That's e to the negative k. And I want to solve for k. I'm trying to figure out what this constant k is. So to solve for k now, I would probably just take the logarithm of both sides, because that's how I can cancel the e. So if I do that, I'll just get negative k is equal to the log of 1/2. And actually, that means that k is actually the natural log of 2. There's a 2 to the negative 1 power. Right, this is 2 to the negative 1 power, so you can pull the minus out and cancel it with the other minus and just get a natural log of 2. You're going to need a calculator to get a final conclusion to this. But the point is that the temperature of the body, we now have the full expression for it. It's 34 plus 4 times e to the negative ln of 2 times little t. This is it. That's what we would have. And we're just about ready to answer the question now. Normal body temperature is 98. So what you need to do now, guys, is put 98 over here for the temperature and solve it back now. Now you have to solve for the little t. Okay, so you put 98 in on the left side there. So from there, you just need to subtract 34, then divide by 4, then take the logarithm and so on and solve for t. And you should find out that if you do it correctly, I will let you do it because it's really just a calculator exercise. You should get t equal to -4. If you do the logarithms and calculations correctly on your calculator, I hope that you will get t equals -4. If you don't, you can come check your work with me later. But that means that the time of death was 10 a.m., right? 4 hours before the clock started, which was at 2 p.m. 4 hours prior to that, that's why I'm going prior because of the negative. 4 hours before 2 p.m. would have been 10 a.m., right? So that is the answer. What is the time of death? 10 a.m. Okay, just make some sense? Nice. Great. If everybody's good with that, are there any other questions on the homework that's due tonight as of so far? These are both from section 1.4. I just wanted to make sure. If you're still working on it, of course, we have the whole rest of today to work on it too. And I have a lot of office hours. So if you need to chat with me offline later, we can also do that. Everybody good? Okay. For now, I guess I'll leave it at that. So I know that you guys all watched my syllabus video, the part where I talked about the pop quizzes. These are 25% of the grade for the semester. I've decided to go ahead and have one today to make sure that everybody's doing well with the material. So no pressure here. This will be it's about the same as like an exam. Pass these out. Is everybody getting nervous? You know, I like to play tricks on you though. Go. Guys, this is not a pop quiz. Sorry. I didn't mean to do that to you. Well, I did mean to do it. I just had to have a little bit of fun with this. I don't give pop quizzes. I don't think I was in the syllabus video, right? It's, you guys, did I have you thinking it was a quiz? I actually kept a straight face. Okay, no, I don't do pop quizzes, definitely not. This is something totally different. I did mention, I think in my syllabus video, that I like to have you guys practice the material a little bit with one another. Instead of just listening to me for 2 hours every single day, I like to have you guys actively practicing the material a little bit. So here's what we're gonna do. This says group work number 3 on it. You might be like, well, where was group work number 1 and group work number 2? Well, actually, those were part of the videos that you watched last week. I actually kind of did those problems already for you. So we're already jumping into number 3 here. These, unlike any pop quiz that I was trying to get away with, these are not graded. This is just for fun. And also the solutions and these handouts. So for the whole next 4 months, if you ever want to go back and review these and look at the solutions or practice or whatever, you'll be able to do that. So what we're going to do, for that reason, I'm not necessarily going to give you a massive amount of time to do these problems. So what I'd like you to do is don't worry about if you don't finish, okay? But I would like you to grab 2 or 3 other people in the class, and to the extent that we can, there's a whiteboard back there. We've got a lot of room up here in the front and on the side. I'd like to get everybody kind of out of their chairs with their group, 2 or 3 people. And on these 3 problems, the first thing I want you to do, before you try to solve any of these problems, I just want you to try with your group to decide, is it separable? Is it linear? Is it Bernoulli? Is it homogeneous? Let's just do that much. And then if you have a little more time, I'm not gonna give you a lot of time, but if you have a little more time, your group can just pick any one of them that you want, maybe want to actually try to work through the solution of using the methods that we talked about on Tuesday. Okay, so does that make sense? This is your chance, if you don't know anybody else in the class, find somebody close to you that you can just kind of join their group. Let's have groups of 3 or 4 people. Let's get everybody up. First up, we've got to stand up and we can come all the way around and find a nice spot on the board. And I'll come around and give you a hand. And please write your names on the board as well.
My name's Isaac.
Come on down, guys. You can use this space right here.
We was just corner.
First with them.
You guys can come up and there's gonna be articles from. I'll get out of the way.
You think the second one's interview?
Why primes is that's why where these
I think the second one might be better.
Well, I mean,
But right here, it's the, that's why primes is one. Yeah, I think it's times y. Volleyball, there's also a y in there.
So if you divide both sides by 3x minus 2. And then multiply all of the x's and y's by t with that, like, if you like y factor out the t, be the exact same.
You can all write your names down on the board too. Just so I have them down. Is yours like IS?
Yeah.
And
So if you would, so I think you have to divide the three. This over here. This going on. You have to divide. This you have to divide. Three y. Over.
Oh.
I can actually write it.
That was a way in. The last. I don't think you can cancel it.
You can.
Okay, it says several, it sounds like proton linear, so it actually might be linear.
Yeah, fine.
Oh, actually, let's keep E. I guess you can just back out the T. Oh, yeah, so it is. Yeah. Okay, so then I guess it.
It's not in the form for.
No, it's not. That's why I was thinking.
So it's, yeah, it's probably.
The y by t.
Yeah, then you can just factor out the C.
This one 3x t.
Not fine. This one doesn't have a Y. That's
it is only half. That's also why it's not linear.
3x.
Yeah, so in between.
Close friends, please. Why is x from v?
See if it works. Everything else out. Hopefully it's all yes. Anybody need a hand? I like that. Oh, yeah. Good answer. So you guys figured out this one was homogeneous. So before you actually solve this one, can I quickly get you to classify number 2 and number 3 first? Let's get them all classified first, and then we'll go back and take time to. That is totally the right answer. How are you doing, team? Certainly is. So before you solve that one, I want you to actually classify all the three. And just so I have this straight, are you?
Oh, yeah.
Oh, I said.
Thank you. Thank you.
Alright. I know, huh, cause there's like a sign. Mm.
I think the other one.
Oh, that's gotta do those as well.
Yeah, we just provide, yeah. I mean, I guess it could be like. Yeah, that's just.
What about the third one? What do you think the third one?
Okay. So I guess. Sure. Whichever one you agree to.
Yeah, that was.
Probably. It was just burning. Well, if you divide by, you'll have to move that. Oh, so actually live here? Yeah. Oh, okay.
And it also gives something, like a fellowship.
Two over.
We'll be negative 2 over.
It makes sense. Oh, no, that's why, Hawaiian.
It was it's probably. Oh, yeah. I don't went over it.
You can write it under Carly.
So we don't need.
So because 1 over x squared times y.
As we have.
No, that's all I need. I guess.
Yeah.
Got it. Perfect.
Squared times y.
Oh. Oh, yeah.
I'm sorry.
Looks great. Number 3. Right integrating here. You guys are doing awesome. Remember that what happens with one function in the derivative becomes equal to the cube of x times So that'll help you, with sort of getting to the next step. Once you have it, that you can go straight to that if you want to. I think you did the five, okay. John did.
You don't need to use any of it.
Yeah.
You can just go straight to it. Yeah.
Well, make sure you divide everything by. Yeah, one over. There you go. Click one. Nice, nice, nice.
Yeah, why? Why?
Oh, no.
No, it's not.
Yeah.
Oh, no, no, your P axis, U axis.
Then. And then you do want to write.
You know.
Yeah.
Oh, yeah.
Yeah, you're just setting it up, right? And then you.
Oh, I see. Yeah. Yeah.
Yeah.
So that's just one of those squared y and then we have to.
Or the.
Yeah. It's I want the, no, it's like.
I didn't, excuse me.
Oh. Oh, no, it's,
You can. Oh, yeah, yeah, it's why.
and then.
Okay, then.
Yeah.
So then that would be one over X.
No, no, you can't do.
I just locked it. So then what?
No, you would just be L and X. I don't know the.
It's like right now, that's the.
Yeah, but. Oh. Oh.
Solve this, right? Yeah, so you would solve it. Remember the change of variables that we did on Tuesday? Y equals 5, 9 equals x squared plus b. Use the way to really this. So change the variables. And then solve it, because remember the data signature would always be separable. So you would turn it into a separable, I don't know if you should solve that yet. Because then you go back and. Okay, and then you can just, it's like, well, that is the for you and for you. I just want you to take it out. You can sign the B. So we can't.
These are both me.
You can hit them up on the board.
Yeah, it's like something, right? X, the y over plus b equals 3b. Y 3 minus 2b. Because like, you could just put all the b's on one side. You put the g first.
Subtracting.
Yeah. It'll be D.
I'm gonna write it out.
Oh, you. Oh, yeah. But it's in the Y on the Y line.
Equals.
You're basically.
Has to be.
Oh, no.
Why so?
Prime. Yeah.
Yeah, I mean, it's true.
Is it divide?
There's no.
Oh, we did.
Divide.
Oh, yeah.
Me, we go. So this is our last, so we figured out we could find out the X, right, so it goes away from this side, completely goes away. We, let's see. You would want to like. Equals three. Now it says PV.
Why not front?
I'll just move this one to the other. Also like to make this. Because what I'm thinking is you're gonna put it.
Warm.
It's got like.
Or homogeneous, you're doing.
Okay.
That's where homogeneous.
Because these pieces are- you know what I'm saying? So we can do this.
Oh, that's why.
You know what I'm saying?
Oh, more 5 hour.
Yeah, so. Yeah.
And then if I move to the other side, please. May not be given to you. And while I'm there, pretty much Robert. And you're German. You're all about. Thanks.
Anybody need a hand?
Oh, and this is also correct. And this is. I think it should be mine. Yeah, this or something. It's just minus you put extra money. If you have this one, you just need that. Or like.
Then here, the B is already minus.
See these
Basically,
you could factor
them,
them, cancel them.
This is two B's.
Now we have, it's still not like that. But we do.
It's the same.
No.
So,
What?
I think, right. And then you just separate them, so now you have all of these, so you flip this function to move to this, it's and then you.
So I'm gonna go ahead and already. do
Yeah.
Just subtract over to this side, right? This B, that's right.
This one?
Dude.
Which one do you like?
And that's because I'm trying to get everything separated.
Oh, yeah.
Side. Yeah, that's what he's gonna call me. I already see that. Separate. Right. The only thing is, this is kind of a pain. So think about this thing, but if we need to just think about
Okay,
it.
so this is just, this is.
Right, what we can do is,
times
basically.
This.
What is it?
The big line money. Minus signs cancels. So it actually must be done. This square
And now on the left side, you still have this.
And then find minus three.
What you'll need to do, of course, is put this, the DB.
Here, wait, what do we?
And then like, yeah, the X and the D axis. Exactly, so the D axis or X will be there, and on this side we'll have.
We can solve. This is all right, because he has three variables, so he has the B and C.
So.
It's very good.
Now,
There's zero.
so this is easy to integrate here. For
Or,
this one, what you would want to do is split this, minus sign. Integrate with a bracket. It's not the.
Yeah, I think it's the-
And then we plug that into the.
Because we know that these integrals,
Not too bad. I have it all. written out.
because we can use that, we.
Yes, absolutely, absolutely. Loving what I'm seeing out of all these groups, we've got a lot of big progress. I think every group had a chance to classify all three of these equations and maybe solve one or two of them. I don't know exactly. I know that nobody really finished, and that's fine. But I would like to go ahead and kind of bring this to a close for now. And what I'm gonna do is give you, remember we always take a 10-minute break? I'm gonna give you a 10-minute break right now. If you wanna use it to keep working, you can, but if you think you're gonna want some fresh air and some stretching your legs time, feel free to do that right now. You can erase it as long as you're happy with it and done with it, if that's good enough for right now. Kent, are you enrolled in the class or are you just waiting? Are you enrolled in this class or are you still waiting?
Like, you know, when this.
Oh, I'm from enrolled. You are enrolled, okay.
And this.
I might be confusing with somebody else. Okay, all right, thank you.
That's how we solve, right? That's what he did. Like, look. See, he changes, once you get, like, he changes it, why? I don't know, because we have two. of these. We have one here and one.
Are you guys in the Discord?
Yeah. You're good to go. All you guys.
Are you doing like the?
Oh, I mean, to get rid of the log.
So much math in the computer science. Like three.
Actually, there's some CS electives that double bill. Like this. So this is literally the only class you really need today.
Dude, I feel cheated. I would feel cheated like doing comp science, just like finishing it out too.
Yeah.
That seems so fucked up, like.
It's funny because I didn't. I got an C.
Yeah.
I didn't come to me, I got an A. It's like, what the-
Calculus, I was like, calculus, dude. I was like, the way you.
And compared to Calc 2, I was like, Jesus.
When we were doing vectors in the first semester, I was like, fuck, I was like, oh shit, this is gonna be as much as.
No, yeah, it was like-
It was partial differential.
I was like surprised people were like struggling. I was like,
Yeah.
oh, man, this is like a cakewalk compared to Calc 2. Well, I went to community college. I just transferred.
This is lucky.
Yeah.
I like some random, like, right time. I forgot his name, I'm not gonna lie. Really? Oh.
A lot of like the kids were like complaining over and over again. Like there was a guy who just like would yell every class like, you don't
understand you?
Yeah, I can. He was a baby.
My first-time guy he was just really like anal about grading and stuff, like he would not change his mind, like really like you argue with him. But like honestly, I think that was pretty fair, so I was like, that's not the worst.
That's when I just want to talk to I had the same teacher. What?
Yeah. Oh, all of the calculuses I've taken, like here, I'll say, have been like that. I always want.
I'm not gonna lie, most of my close professors are pretty like fair, like the content wise for the exams, or like some of them were tricky, but like you definitely learned it, you know?
See, that was my Calc 3 professor.
Yeah.
She was like,
This is so.
Basically, like, you did the home.
I think your best
Or do you got
for outcome, honestly, is ring.
Honestly, this, I'm not, there's a lot good math professors here than CS professors. CS professors like,
Oh, yeah.
like four, maybe like four good. Yeah. I'm third then.
I was gonna double major.
Dude, don't
Like,
oh, really? Damn.
Yeah. It's true, like this is. They're like bad at it. I don't wanna be that.
No,
It's important.
are you gonna double major, you said?
No, I'm just gonna. C's was never. I feel like I'll double major in stats. That would be really fucking cool. But I'm running out of better. Yeah.
I might, they just added data science finder, but it's not even like, oh, you can see it anywhere. You have to like time doc to them. So I might do that one instead of math.
But we'll see. My.
Okay, so you're saying.
Oh, yeah, I'm done playing.
Oh, it's more cheap.
I'm playing on going back. Not that big.
Well, it's still positive. Oh, and then.
Oh, it'd be Ellen. Oh, yeah, it'll be, oh, yeah. Sounds a bit Ellen. Let me see.
Oh, wait, oh, you're done.
Comes one.
Oh, my God.
You did some drastic. What
do you mean? Yes.
Both sides? Yeah. And then it's be L and Y over X.
Wait, but look, since we have a combined function like that, isn't it like, is it not, does it not work if this? It's px times y, so if we're saying that px is two thirds, three.
Y next. The other side.
Huh?
Oh, yeah. Y.
And then, or the end, but like. You subtract this out, or, yeah, if you divide it out, so you have like this. E over N. I'm sorry.
I mean, we could just. The power of real just do.
Why is it the power of three? Or
Or it would be.
oh, you put E, if it, all this is the power of E? Okay, yeah, okay, I get that. Wait, what happened to?
You're just.
Shouldn't it be minus all of this? It's like there's two. We don't have, a random. Is that how it works? Oh, wait, that's that, yeah.
I think it meant like somewhere like.
Still working on.
Yeah, we're committed.
I think we just make stuff up.
Yeah, I don't think.
Unless you really wanna.
Okay, I get this. Yeah. Wait, I got this, so you go from here to here.
We got one of them.
Wait, how did you get rid of this E? No, we got but not this E. Like you got rid of this E right here.
Yeah, cause.
Oh, this LN, yeah.
I just made this.
Yeah, I get it. So you're going here to here?
I wasn't even looking.
Yeah.
Steal this little piece of your desk here. Okay, thank you so much.
Why?
It's.
Oh, yeah.
You can't scoot.
Wait,
Okay. What's that?
Yeah, let's see, but I'm saying this is B, so this is gonna be e to the power of y over x.
Yes.
But doesn't that mean y divided by ex, right? If it's e to the power of y, wait, right? What if it's y over x like that? Is that the same? Or is it gonna be y like this?
No,
Like I said, I mean that no. Well, this is the divided, like the power of y over x, is that equal to this? Are you sure though?
All right, guys, I'm just about gonna have to wrap this up.
You guys were wrong over there.
I think you can still refer you to my solution. How's that? You're doing great. I really appreciate the effort, but I am gonna start.
Yeah.
Second, okay? Thanks. And thank you for your. You guys have, this must be somebody's notebook here. Yours, and this is mine, and this is somebody else's handout, probably yours, okay.
I don't think we.
All right, guys, let's go ahead and again, yeah, so the time I'm gonna get you out of your chairs a little bit and ask you to work with your classmates and see if you can practice the material that we've just been learning. I think it's good to do that rather than just listening to me the whole time, especially for a 2-hour class. I do want to point out, I've got the screen down to show you just that if we go into the files section of Canvas here, there is a folder called GroupWorks as well as another folder called GroupWorks Solutions. So this stuff is never going to be graded. In fact, I've got them already posted for the whole semester. I've got like 15 of these. So the GroupWork 3 that we just did, you can just open this up and review this on your own later. Just the same problems you just worked on, and I've got them kind of all solved out here for you. So I won't go over them in class in detail right now, just because I did type these out for you. But I just want to make sure you know that this stuff is here and it's totally accessible anytime, 24/7 for the next 4 months. So I just wanted to let you know that. But yeah, I do appreciate very much your efforts on that. I think it'll help you learn the material to look at the GroupWorks. Especially also when we get closer to taking an exam in this class, it'll be just nice to maybe review the GroupWorks. You're not gonna wanna go back and like redo all the homework. Obviously, that's gonna be more than you have time for, but looking over the GroupWorks, remember the GroupWorks, these are problems that I wrote. They're problems that I've spent class time on. It must mean that I must think it's a good thing for us to spend some concentration focusing on. So anyway, hopefully that was a useful exercise. The next thing I'd like to do really quick before I get back into math, I've got a recap over here. So if you haven't had a chance to jot this down yet or take a picture of it, I would recommend that you do that. But before I actually start talking about that, I'd like to just go through the attendance roster again today, one more time, just to kind of see if people are still showing up and if there's going to be extra space for the wait list and so on. So let me do that right now. Is Mohammed here today? There he is. How about Daniel Bernal? All right. Angela, great. Melody, thank you. And Cameron, awesome. Is Blake here today? Blake's here, awesome. Johnson, thank you. And Adam Garcia, gotcha. Julia, thank you. Sarah, I don't think is here, right? No Sarah today. Christian Hernandez, there he is, gotcha. And Isaac, thank you, Isaac. Austin, thank you. Audrey's here, I saw her. Marco is not here, I don't think. Robert Lopez, thank you, Robert. And Ryan, great. Derek, is Derek here? I think I saw Derek today. Gwendolyn is here. And Bryce is here, gotcha. Nathan is here. Thomas is somewhere, I saw him, there he is. Kira? Yara. Let me just see. Okay, got it. Jason is here. Gerardo is somewhere. There he is. Thank you, Gerardo. Bryant, gotcha. Eric Salvador? No, okay. Alex is here. And Kent was somewhere. There he is. Thank you. Jerry. Leo, is Leo here? There he is. Thank you, Leo. And Eduardo is here. Antonio. Thanks, Antonio. And Daniel Ventura. Gotcha. And Gilbert is here. Okay. Is there anybody here whose name I did not just call? Got it, everybody. Okay. Perfect. Oh, well, Min, you're here. Should I write that down as well? Okay, perfect. I think we're looking pretty good on that part. All right, well, what I'd like to do for the rest of today is pick back up where we left off on Tuesday. Remember, we did this massive change over to linear algebra. And I know we still have some leftover chapter 1 stuff, the Bernoulli and homogeneous differential equations. That's the homework you're going to be doing for Monday now. So over the weekend, you'll work on that. So we've got a little loose ends with that still to go. But for the most part, we're launching headlong into linear algebra for the next 10 weeks approximately. And this is the part that I absolutely love more than anything else. So we're working a lot with matrices, right? And we talked about it on Tuesday. An M by N matrix is just an array of numbers or functions, and they're arranged in rows and columns, the entries, right? So capital A is a good notation for a matrix. And we initially were talking about matrices because they were going to help us to solve linear systems. So I'm hoping I'll be able to explain more about that before we get out of here today. But before I go back to the systems of equations that we want to solve, I want to spend a little bit of time just talking about raw matrices. Just what can we do with matrices? Just kind of get the basics down on matrices. So I did start this on Tuesday. I kind of ran out of time at the end, so I'm bringing it back up again here. There's some certain operations on matrices that, are very common that we like to do. One of them, which on the surface may seem like a silly thing to do, but actually is quite common in statistics and approximation theory and a bunch of other mathematical fields. This idea of taking a transpose of a matrix. This is where you just swap the rows and the columns. So whatever the rows were, which were written down horizontally, you just recopy them now vertically, right? So the whole array gets kind of tilted on its side. It becomes a different size matrix, yeah? It becomes an N by M matrix. So N rows and M columns for the transpose. Of course, if the matrix has the same value for M and N, then the size wouldn't change in that case. It's still just N by N, but the numbers will still get swapped around within that transpose matrix. Okay, so that's one thing that we mentioned briefly on Monday. We will see the transpose from time to time throughout the linear algebra. Another thing we can do, and this is really only interesting if the entries of the matrix are functions, but we can do calculus on a matrix. We can take a derivative of a matrix. We can take an integral of a matrix. Here I've written the integral as an indefinite integral, but you could also do a definite integral with limits. And just what you do is you just do slot by slot operations. So if I ask you to take the derivative of a matrix, that just means you're going to go to each and every entry of the matrix and take the derivative of whatever is in that entry. You're just going to do that all the way through the whole matrix, right? Same thing with integration. Integration is slot by slot. You just go through every entry of the matrix and just integrate whatever was in each slot separately from every other entry. It's kind of just common sense what you would do if you just had to take a guess at it. That's probably what you would do. Okay, kind of just do it slot by slot. So that's pretty easy. We will be doing a little bit of this calculus with matrices,
more later on, when we go back to differential equations, is where we'll see more of that happening. But right now, since we're really focusing on just raw linear algebra, most of the matrices that we look at are just going to have numbers in them. Right? Even on Tuesday, what did we do? We wrote down a system of equations and then we wrote down the matrix. Well, that matrix just had numbers in it. It was just the coefficients of the linear system, if you'll recall that, right? So if the matrix just has a bunch of numbers in it, then calculus isn't so interesting, right? Taking derivatives and integrals of just numbers is not much to that, and it's not really that relevant for right now. But we will see calculus coming back in, well, when we go back to differential equations, which is not until chapter 8. So we have a long way to go till we get to that. The more relevant point for us today is actually the third one here. This is where we're going to be spending most of our time here in chapter 2, which is the algebra of matrices, right? How we can just do regular algebra. And when I think about algebra, yeah, I think about operations like addition, subtraction, scalar multiplication, and multiplication. The first three of these, the addition, the subtraction, and the scalar multiplication, are, again, just extremely natural. You just do slot by slot calculations. Of course, that's going to require that the matrix, if I'm adding two matrices here, like if I want to do like A plus B, that isn't going to make sense if the matrices don't have the same size. I can't take like a 2x4 matrix and add it to a 5x7 matrix. You just can't line up the slots that way, right? So they have to at least have the same size, and same thing with subtraction, right? So the matrices must have the same size here. I'm not writing a lot of real detailed notes on this, guys, only because, you know, it really is just kind of the natural common sense thing. Like, you can't hardly mess this up. You know, if you wrote down two matrices that weren't the same size and then you tried to put a plus sign between them, you'd start scratching your head like, oh, now what do I do with this? It doesn't make sense, right? So it's got to make sense for you to be able to do some of these operations here. Scalar multiplication, this is just taking a scalar. A scalar is just another word for number. You just take a number and throw it through every single slot of the matrix. So you just multiply it into every single entry of the matrix. Nothing bizarre here at all. In fact, I would almost, can I use the word boring in math in the same sentence? It's almost boring, right? It's like you just don't even have to think that hard, and you just do the natural operations, okay? But it turns out that the story does start to get a little bit more interesting when we go to just regular multiplication. So scalar multiplication is where we're taking a number times a matrix. That's no big deal. You just take the entries of the matrix and multiply all of them by that number. I'll call it K, right? That's pretty standard. But what's weird, and maybe some of you have seen it already, but I'm going to go over it briefly now. What's weird is if you want to multiply two matrices together. The first thing that's weird about it is that the matrices that you're going to multiply together, they don't have to be the same size. And we don't multiply matrices by just doing slot by slot multiplication. There's kind of a different way that we multiply matrices together. So I need to kind of explain that now. So I'd like to go through this. I'm going to go through it fairly quickly. I'll do maybe one example of it. If at the end of that, you know, I'll obviously take some questions, but if it's still kind of not coming to light very easily, I will probably just say, go to the internet and look for any video about multiplying matrices together, because there's a billion of them out there. I've definitely checked that. And so it's very easy to find examples of this. But let's talk about, let me briefly do it for you here. Matrix multiplication. Are there any questions so far though, by the way? I'm totally good with questions. I should make sure I remind everybody of that. You know, I like having this interaction with the audience. I taught for like 3 semesters straight during COVID when I was talking to people through the computer or these little boxes and pictures in Zoom. And that was very hard because I couldn't tell how people were doing with the material and people weren't asking questions. And it was just really, the communication was a little bit tough. So it's really nice to be able to be in the same room and hopefully clear up any confusion if you have any, okay, as we go along here. So let's see if this makes sense. So some of you, like I said, if you've already seen this, just bear with me as I explain this. But what we're going to do here, guys, is we're going to talk about multiplying 2 matrices. So let's say we are given a matrix capital A, which is M by N. So I'll put the size of the matrix here. And we take another matrix, which I'll call capital B. And B is going to have a different size. Notice the size of matrix B is going to be N by P. Okay, so A is M by N and B is N by P. These 2 values right here, the N's there, those must agree. Okay, so that's going to be the first thing, is that the number of, what is it? The number of columns of the first matrix has to match the number of rows in the second matrix, which is N here. Okay, so then we can form the matrix A times B. And this matrix will have a size which is going to be M by P. Okay, so it's even a different result. So the M and the P, right, the rows of the first matrix and the columns of the second matrix ultimately dictates the size of the product A times B. But in order for this to even make sense, the N that was in the middle here, the columns of the matrix A and the rows of the matrix B, they have to agree. If they don't agree, then we cannot form this matrix, okay? And now, how do we form the matrix would obviously be the thing we need to talk about here. I'm going to explain that by doing an example, okay? Instead of, you can read it in the book and it's a lot of notation has to be written down with like subscripts and like entries of the individual matrices. It gets a little bit tedious to write it down. So I actually would prefer to just show this, if you don't mind, with an example, okay? How this works. This is basically the definition of it. This is how it's defined. So let's do an example. I'm going to take a matrix A, and this is going to be a matrix with 2 rows and 3 columns. So it is the matrix 1, 2, 3. And then the second row is 4, 5, 6. And then I'm going to take another matrix B, and B is going to actually have 3 rows. So the first row is -1, 0, 2, and 1. The second row is going to be 2, 1, 1, and 0. And the third row is -1, 3, 0, and 1. This is what I want to do. Okay, so I am going to try to explain now how to calculate A times B. Actually, before we do that, we should make sure, can we even calculate A times B? Let's get the sizes of these matrices. What is the size of the matrix A that I've got on the board here? What by what? 2 by 3. Great. 2 rows, 3 columns. Okay, very good. What is the size of the matrix B? 3 rows and 4 columns. 3 by 4. Very good. So notice that the 3s, right, they agree, right? The 3s agree. So that's like the N value. And the result of A times B, can somebody tell me what will be the size of A times B? 2 rows and 4 columns, right? The M is 2, this is M, and the P is 4. So 2 by 4 is what we're expecting. So let me set myself up to write down a 2 by 4 matrix. 2 rows and 4 columns. That's what we should get. Now, how do we do the entries of the matrix? What we're going to do
let's say we want to find the 1-1 entry, right? The first row, first column entry here. What we actually have to do is a dot product. Do you guys remember from calculus 3, third semester calculus? You can take a vector. I can treat the first row of this matrix as a vector. And the first column of the second matrix is also like a vector. And by the way, because the 3 and the 3 agree, these two vectors both have the same number of slots. 3 slots here and 3 slots here. That's because these numbers agree. That's why that's working out. And I can take a dot product, good old classic dot product from calculus, and get a number out of that. Let me just do this dot product, right? 1 times -1 plus 2 times 2 plus 3 times -1. That's how we do a dot product in our familiar calculus context, right? So that's going to be what? -1 plus 4 plus -3. What's that add up to? 0, right? Just going to be 0. And that's the number that you put there. That's the 1-1 entry of the matrix A times B. Notice I use the first row and first column to get that 1-1 entry. If I wanted to get the 1-2 entry, the entry in the first row, second column, well, now I'm going to keep the first row here, but I'm going to shift over and use the second column to do my dot product this time, right? So at this time, I'm going to get 1 times 0 plus 2 times 1 plus 3 times 3, right? So that's 0 plus 2 plus 9. What's that add up to? 11. Thank you. 11. So that's 11. That's the 1-2 entry. Okay. The entry in row 1, column 2. Why don't you guys try the next? Let's try to finish out the first row. I'm going to take the 1, 2, 3 row and I'm going to dot it with each of the third and fourth columns to get these next two numbers. I'm going to give you 30 seconds to do that. See if you can fill out the rest of that row. Just doing dot products. Does anybody think they have it? What are these two numbers? 4 and 4. Exactly. Beautiful. Okay, we remember how to do the dot products from calculus. That's really what this is about, right? So we should just get 4 and 4, right? So we have 2 plus 2 plus 0, which gives me 4 right here. And then for the last entry, we have 1 plus 0 plus 3. That also adds up to 4. Okay. What do you suppose I'm going to do? Is that okay? Sure. Okay. What do you suppose I'm going to do differently to get the second row? Okay, we're going to have to do slightly better mental arithmetic because we're now going to use the second row and dot it with all of the other columns. So now the numbers are slightly bigger. Okay. All right. You have 1 minute. I want you to try to fill out the second row of this matrix. Take the 4, 5, 6 and dot it with each of the 4 columns and see what kind of numbers we come up with. Okay, I see a few people have kind of already got this spelled out, so I'm gonna go ahead and jump in here. Right, when I take the 4, 5, 6 and I dot it with this first column, 4 times -1 plus 5 times 2 plus 6 times -1, that's just -4 plus 10 minus 6. That's 0 as well. Get another 0 out of that. And then if I go to the second column, I have 0 plus 5 plus 18, that's 23. The next column is 8 plus 5 plus 0, which is 13. And the last one is 4 plus 0 plus 6, which is 10. You can get pretty fast and furious with this after you've practiced it a while. But it's just dot products, really all it is. Okay. So that's how the matrix multiplication works. You might be wondering why we multiply matrices like that instead of just some kind of a slot by slot thing. It has to do with the fact that we can represent a matrix. We're going to talk about this when we get to chapter 6. We can represent a matrix as a function. It can actually be viewed as the mechanism of a function. And what we want is composition of functions to be somehow in agreement with how we multiply matrices. And if we do it this way, that actually does happen. So that's kind of a little bit above where we're at right now, but there is definitely a reason why we multiply matrices the way that we do. Okay. Any questions on that? I know it was a little quick. I'll just have you watch some videos of people multiplying matrices together. This is all over the internet for sure. You can definitely get plenty of practice with it. I do want to ask you a question here. This is kind of an interesting one. What would be, if we took the same two matrices, what if I wanted to do B times A? So in other words, put this one on the left and then put this one on the right. Can I do that?
No.
Right?
Your dot products are the same.
Well, let's take a look. See, the thing is, if I put the B over here, it's got 3 rows and 4 columns. And then if I put the A right here, which is just 2 by 3, these rows, remember you have to go across the rows of the first matrix and you have to go down the columns of the second matrix. Will these be compatible? Can I take 4 numbers across here and dot them with 2 numbers down this way? Not so much, right? The problem with this, of course, is that in this case, the B is 3 by 4 and the A is 2 by 3. And these 2 numbers, right? These 2 numbers, but if we say here, the numbers in the middle have to agree with each other. And if we set this up like so, this doesn't work anymore. Right? So the answer here is that this is actually not even possible. This is not even possible to do that matrix multiplication. Oh boy. So that means that in general, I'm about to tell you about a property that we take this for granted. When we're working with numbers, of course, we can multiply them however we want. But in general, for matrices, if we do A times B, there's no reason to expect it to be the same as B times A. Those definitely could be different, right? They may not agree at all. And in other words, what we're saying here is matrix multiplication is not commutative. So this is the algebraic property that commutative just means you can multiply everything in whatever order you want. But with matrices, we can't be quite so sloppy with it. We have to write something in the same order. So for example, if I had, let's say I had a bunch of things that I wanted to multiply together. Let's say I wanted to do A times B times A, maybe there's another matrix C times B times A times B times A. If I had a bunch of matrices to multiply together, you can't simplify that. Right? You can't like say, oh, well, that's A to the 4th and B cubed or anything like that. You have to leave it as AB, AC, B, A, B, A, right? Right? This cannot be simplified.
This cannot be simplified. Yeah, Johnson.
What if, interested for 3x3?
What if, great question, what if they were both the same size? And they were both like n by n? Then we could actually multiply them in either order, but even so, the actual dot product calculations would usually, unless you got lucky, they would usually be different depending on which matrix was first and which matrix was second. So this non-commutativity is pretty pervasive with matrix multiplication. Even when you can multiply them in either order, chances are very low that A times B would ever be equal to B times A. It's just the way it is. Okay, you know, so if I had something, we can talk about squaring a matrix. So I can take, let's say I take A plus B. Let's say they're both 3x3, right? So this could be n by n or whatever. And let's just say I want to square this, right? You know, I can think of that as A plus B times A plus B, right? The quantity A plus B times the quantity A plus B. And yes, I can go ahead and FOIL this out the way you would if you were doing an algebra class in high school with numbers. You can FOIL this out, A times A, which is A squared, and then A times B, which is the outer term, and then the inner term is B times A, and then the last term is B squared. But if you were doing this with numbers, you would probably take the middle terms and write it as 2AB. You like combine them together, but here you cannot do that. Again, this has to be kind of left unsimplified, right? So again, this cannot be simplified. So this is most people's first ever experience with non-commutative algebra, where the algebra just does not commute. You can't just switch the order of stuff, right? I can't tell you how many times this has happened so many times. I've taught the class a lot, and I'll see people do stuff like this. Here's a matrix B and it's equal to C. And I'll see people say, oh, I'm going to multiply both sides through by another matrix A, and they'll do this. So I'm just going to multiply through by A, right? If B is equal to C, then isn't AB equal to CA? Well, the answer is no. You cannot do this because notice what I did is I multiplied on the left. That I put the A on the left over here, but I put the A on the right over here. That's not correct. I would have to do the A on the left on both sides. Then it's okay. Right, then I can get away with that. So just be careful. You know, unfortunately with matrices, we do have to watch out for stuff like that. It just doesn't work as nicely as we might like it. Okay. Questions? So we talked about addition, subtraction, scalar multiplication, the multiplication being a little bit weird as we just discussed. The one thing that is missing from the board, of course, is division. Because usually you would think addition, subtraction, multiplication, and division, which is what you do with numbers. As it turns out, guys, we cannot divide matrices. Can't do it. I have a substitute for that, though, and I'll tell you about it next week. I'm going to make you stew over it for the weekend before we can actually explain what can take the place of division. But for right now, we're just going to do addition and subtraction and regular multiplication and scalar multiplication. Okay. Just a quick definition, you know, I'm still kind of in this preliminary section of matrix theory. A matrix is called square if it has size n by n. It's called square if it has size n by n. So that kind of makes sense. If there's the same number of rows as columns, then when you sort of draw it out, it'll kind of fill out the shape of a square. So this is sometimes called a square matrix. Once we have a square matrix, there's a lot of other vocabulary associated with square matrices. We can talk about a square matrix being symmetric or upper triangular or lower triangle. There's all these words that we have. I actually put together a handout on those terms. And then the handout, I felt pretty good about that, but then I decided I wanted to do even better than that. So I made a little 7-minute video about these like special matrices that we have. I'm going to ask you to watch that video over this weekend and take some notes on it for me. I would do it here, except it's really, really basic stuff. And I would rather focus on the stuff that's maybe a little more interesting for what we're going to be doing. So let me just say in your notes here, see video about this. Well, and I can point out, I think I did this last time. Let me just go back and pull up my screen again. So, yeah, there we go. Yeah, so I just wanted to show you again that I have a lot of videos, and I will from time to time ask you to watch 1 or 2 of these. If we go to pages, remember there's this section called additional videos. So I'll show you where it is. I'll send you an email with this special N by N matrices. This one right here. It's a little 7-minute video. So I'll have you watch that and take some notes on it. Fill in a little bit of space. So you might want to leave a little bit of space in your notes if you want to put the notes in the same spot. Otherwise, it doesn't really matter that much. Where you want. Okay. So we are going to talk about symmetric and triangular matrices. So it's not like this is just some like side topic that doesn't matter. We actually really do need it. So but I'm just going to let you guys watch that one. I think it'll save us a little bit of time. Okay. Yeah, so we talked about non-commutativity of matrix multiplication. I do want to say that there are some good properties of matrix algebra. There's a lot of properties that do work the way you would hope that they would work. And I'm going to write them down here. I'm going to make a little list for you here. Properties of matrix algebra. We'll talk about a few of these right here, right now. So the first one is just, this is also, I'm going to go really quick through this. Like if you take any matrix whatsoever and you add the 0 matrix to it. So let's just say that A is M by N. And then we add these. So this is one of the special matrices that's in the video that I'm going to have you watch. This is just a matrix of all zeros. So you can imagine what happens when you add that to anything else. What are you going to get? You're just going to get the same matrix back again, right? It doesn't do anything. So A plus 0 is just equal to A. The only thing is, we're doing it now with a matrix instead of with numbers. Okay, so no biggie, no big deal there. Another thing is if you took 0 as a scalar and then multiply that onto a matrix A. Now you have to understand when I write this 0 here in front like this, I'm talking about the number 0. So if I take 0, remember how scalar multiplication works? We just multiply that scalar all the way through every single slot of the matrix. What are you going to end up with? The 0 matrix. Exactly. Every single entry will become zeroed out by that multiplication. Totally to be expected. Okay, another property of matrix algebra, although it's not commutative, matrix multiplication is associative. So the good thing here is that if you had 3 matrices, A and B and C, and assuming that you could actually multiply them together consecutively like that, then if you first calculate A times B, and take that result and multiply it by C, it will be the same as if you first figure out what B times C is, and then pre-multiply that by A. The key thing here, though, is I didn't change the order of anything, right? A is first, then B, then C. A, then B, then C. But parentheses don't matter. So like an expression like this, A, B, A, C, B, A, B, A, right? This cannot be confused, right? We actually don't have to worry, well, did he do the A times the B and then A times the C and then do this one? Or like, you don't have to do all that. You don't have to worry about all of that because this property actually tells us that parentheses don't matter. So you can kind of leave them out when you're doing something like that. This is really nasty to prove, by the way. Like the notation of it, like you're doing these crazy matrix multiplication dot products, and then you're doing it sort of within itself, like a second time. It becomes. I had to write it out for the book. I didn't like it. It's really tedious. It's one of those proofs that's not very interesting. You don't really learn a lot from it, but technically a mathematician would be like, yeah, I guess I have to go through it and do it. Well, we're not going to do it. Definitely not going to do it. Yes, question.
What if, for example,
It's not here. In the note I'm writing right here, the C, the A, the B, and the C are supposed to be viewed as matrices. Yeah, maybe I should even say this up here. You know, let A, B, and C be matrices of compatible sizes. So they have to have sizes that make sense, yeah, for these things to work. Okay, write down a couple more properties here. There's also a so-called distributive property, which you also have for regular algebra, where you take a matrix A times the quantity B plus C. And this one is really nice. It's exactly what you would hope it is. You just literally distribute the thing out. AB plus AC. Okay, so that makes good sense, I think. And since we do have this non-commutativity issue, we actually have to write down a similar property with the addition on the left side of the multiplication, because the left and right doesn't always work the same according to the box here in the middle. But luckily, at least we can still distribute this exactly as we would in a high school algebra class. So the quantity A plus B times C is just AC plus BC. So that's just totally what you would expect. No real surprises there. A couple more things real quick, and then we'll be good to go. Number 6 here. These last 3 that I'm going to write down have to do with the transpose again. Do you remember the transpose is where we swap the rows and columns here? Can somebody tell me, what do you think we're going to get if we took A transpose and then transposed that? So if I swap the rows and columns and then I just swap them back again, I should get back to A, right? That's no surprise, right? That's not a surprise at all. So very straightforward there. The transpose of A just gets me back to A again. Very good. And then the next one is, what if we had A plus B and we wanted to transpose that? Numbers out of the way here a little bit. So what's going on here is I'm first adding 2 matrices together, and then I'm swapping the rows of the result with the columns. Does anybody think there might be another reasonable way to get to the same place, or to get to the same answer?
You can just transpose them both first.
Exactly. I could just transpose A and then transpose B, and in other words, swap them individually and then add the results. Totally reasonable. That's totally reasonable, and that is correct. Okay. And then one last one here would be, again, having to do with transpose. If I wanted to transpose A times B, we could ask ourselves what this would be equal to. Does anybody have a guess here? Mohammed?
Let's be here.
One more time?
B, A, we switch them.
Ah, you've seen this before. This is a little tricky. Yeah, usually people will tell me that this is going to be A transpose times B transpose. It's actually not. It actually has to be switched. You're absolutely right. You have to switch them, transpose them individually, but then multiply them in the opposite order. Isn't that weird? I think I could convince you though. I try. So like if A is M by N and B is N by P, then A times B, as we already talked about, this is M by P. And so if I transpose that, it becomes P by M. But if I transpose the matrices separately, A transpose would be N by M, and B transpose would be P by N, right? Switching the rows and columns. Now the question is, how could you take these two matrices and get something that is the same as a P by M result here on the left? Well, if I want to get something that's P by M, I actually have to put the B transpose on the left and the A transpose on the right, don't I? It doesn't make sense. Actually, you wouldn't be allowed. You wouldn't be allowed to take A transpose times B transpose. It wouldn't work because these two numbers don't match. Right, so you wouldn't be able to multiply A transpose. It wouldn't even make sense to do A transpose times B transpose. But if you switch the order of it, and put the B transpose first and then the A transpose, everything suddenly works beautifully again. Question, yeah, Blake.
What is the difference between a matrix and a vector?
Oh, good question. A vector is a matrix that has only one row or one column. Normally, that's the way you would think about it. So if I had only one row, if I had a matrix that was 1 by 5, I could call it a 1 by 5 matrix, but I could also call it a vector, and I think people would be comfortable with that. Yeah. Actually, though, you're treading dangerously close to the concept of a vector space, which is in chapter 4, which is always everybody's favorite topic in Math 250B. I'm being sarcastic, but anyway, that in that context, pretty much anything can be a vector, and that's like living in some weird, crazy universe. We'll come back to that at the end of the month. I don't want to ruin everybody's day today. start talking about vector spaces now. Yes, Mohammed.
Would A be equal to BA transpose?
Nope. Unfortunately, A times B and B times A can be completely unrelated to each other and have no, there's no way to sort of salvage this formula and create something that works. It just, when you switch the order of things, suddenly you don't get a result that makes anything to do with the original result. It's just the way it is. I'm sorry to say. Good questions, guys. Other questions? Any concerns so far? I know this is kind of, it's just a lot of basic algebra with matrices. Kind of just have to puff our way through it a little bit. I'm gonna try to take just these last few minutes today and talk about sort of where we're gonna go with this next, and kind of start moving in. Everything I've said so far is like half of chapter 2. And we're gonna be talking next, I'm gonna start this right now, in section 2.4. I'd like to talk a little bit about something called EROs and REFs. And this is the way I'm going to refer to this. This is getting back to the business of solving systems of equations now, right? The whole reason we were bringing matrices up was that they were going to help us solve linear systems. And I took this big detour to talk about properties of matrix algebra. But one thing for sure is that we want to use these matrices as a tool to do something very important, which is to solve linear systems. Okay, so I'm going to get started on this with 3 remarks. So we'll make 3 observations here. And then we'll obviously have to come back to this next week and talk some more and practice some more, but I want to kind of at least get your feet wet with this so that you're familiar with it. So the first remark is that a linear system, and I'll write down an example in a second, but let's just get the comment up here first. It is easy to solve. A linear system is easy to solve by so-called back substitution. This is the phrase that we have for that. A linear system is easy to solve by back substitution if it is in a quote unquote triangular form. If it is in a triangular form, then it would be easy to solve by back substitution. Let me give you an example, so maybe hopefully you would believe this. As a quick example of this first remark, suppose that we had 2x minus 3y plus z equals 6. And then the second equation, maybe this is 4y minus z is equal to 8. And then the third equation, maybe it's going to be z equals 4. There's kind of a triangle here. If you use your imagination on the left side, notice that in the second equation, there's no x term. And in the third equation, there's no x or y terms. But if I asked you to solve that for x, y, and z, remember, you can't always solve a linear system. Maybe it doesn't have a solution, but I bet in this case it does, and I bet you could figure out how to solve it. If I asked you to solve this for x, y, and z, how might you do that? Go ahead.
Plug C equals 4 to the second equation, solve for y, and then plug them both into the first equation.
And solve for x, exactly. So this is what back substitution is. You start at the bottom, you say, okay, I already know that z is 4. If I plug that in here, right, if I plug z equals 4 in here, notice that what we'll get is 4y minus 4 equals 8, and we can quickly figure out that y is equal to 3. Okay, and then once I know what y is, I go back to the first equation, and I can quickly write down what x is, because 2x minus 3 times y, which was 3, plus z, which was 4, is equal to 6. And I will let you do the quick arithmetic on that, but you'll quickly get that x is 11 over 2. So you can solve for x, y, and z. And so your solution here, the solution in this for this problem would be, and here's how we're going to start writing these things next week, guys. I'm going to go ahead and get you into some good habits early on. We're going to use these like braces here. And then inside the parentheses, we're going to put the values of the unknowns. So we're solving for those unknowns, x, y, and z. We should put them in the proper order. So the first one is the x, the second one is the y, and the third one is the z. Okay, so that is an example that I hope kind of illustrates my first remark. A system will be easy to solve it if it's kind of in this triangular form already. Okay, so that's kind of the first observation. Let me write down one more remark for now, and then we'll probably have to come back to this next time, but I'll just at least write it down and we can think about it a little bit. Again, about linear systems. So no solutions to a linear system. No solutions to a linear system are gained or lost. No solutions are gained or lost if we perform
So no solutions to the linear system are gained or lost if we perform these elementary row operations. And by the way, elementary row operations, that's what ERO is an acronym for. So if you're wondering what all these words mean, EROs are just elementary row operations, which is part of what this section is about. So there are 3 of them here, guys. Do I have time to do this? Not really. I don't really have time to even practice it. The idea is going to be, let me just tell you where we're gonna go with this. We'll come back to this. The idea is going to be most linear systems are not in this nice triangular form to begin with. So what we're going to do is we're going to try to use these elementary row operations to sort of tweak our system and do some operations on our system to make it become triangular. That's gonna be the idea behind it, but it's gonna take me another 10 minutes, like write this down and show you an example, so we'll just wait till next week to do that, we have plenty of time. So we'll just go ahead and call it a day for now. Guys, thank you so much for your attention and all the good questions and the group work, I love it. I'm around all day, so if you've got questions, you wanna talk about homework or just anything in the class, feel free to stop by. Have a good day, stay cool out there, stay hydrated. Drink a lot of water.
Thank you.
Have a great day.
You too.
Thank you.